Hello, welcome to Computational Graphs and Backpropagation. So here's an overview of what we're going to be talking about today. First, computational graphs. Second, forward pass. Third, backward differentiation. And finally, backpropagation and how it applies to gradient descent. You're going to see in this tutorial that forward pass and backward differentiation are used in backpropagation. So here's a computational graph, and it's a representation of the process of computing a mathematical expression in which the computation is broken down into separate operations, each of which is modeled as a node in the graph. So you see the inputs x, y, and z. Then there's an intermediate layer, x plus y as expressed by a. And then finally an outer layer, L, which is a times z, right? So you could see that basically some of these operations are decomposed, right? The function is decomposed into two components. Now here's a forward pass. The forward pass is the process of taking inputs and passing them forward through the network's layer or computational graph to produce an output, usually a prediction or loss. Now, this is important in neural networks, okay? This idea of pushing it forward in the network layers, okay, to produce that output, right? So we have L is equal to x plus y times z. We saw earlier that A is equal to x plus y. We could summarize x plus y by putting in a variable. We've got x is equal to 2, y is equal to 3, and z is equal to 4. That's represented by x, this node, the y node, and then the z node. Now x and z, x goes to a is equal to 2 plus 3, and we saw this earlier, right? Y also goes into this node, right? Because it's x plus y. Right? So this is a combination of x plus y. And then finally, z is equal to L is 5 times 4. Okay? So that's the forward pass. Now, what's the backward pass? Backward pass is the phase of computation in which we propagate gradients backward through a computational graph to compute how each parameter contributed to the final loss. It's literally the process of applying the chain rule through a graph of operations. And we saw the idea of chain rule in an earlier tutorial regarding this subject matter. Now we have x is equal to 2, y is equal to 3, and z is equal to 4. Recall earlier, though, a is equal to 5, right? X plus y, 2 plus 3 is equal to 5. First, we have node 1, which is L is equal to a times z. Now, if we take the derivative of this, L with respect to a, and L with respect to z, we get L with respect to z is equal to 5, right? And then we get with L with respect to a is equal to 4, okay? A with respect to x is equal to 1. The derivative of a with respect to y is equal to 1 as well. So in order to calculate L with respect to y, the derivative of L with respect to y, we would calculate L with respect to a and then a with respect to y, and that's 4 times 1. And we saw that we calculated LA, L with respect to A is equal to 4, A with respect to Y is equal to 1. And if we want to calculate L with respect to X, we've got L with respect to A times A with respect to X is equal to 4. Now let's talk about backpropagation. Backpropagation is the algorithm used to compute gradients efficiently in a neural network. It works in two passes. First, the forward pass, compute the output and store intermediate values. And then the second, the backward pass, apply the chain rule to compute how much each parameter contributed to the final loss, i.e. we just compute derivatives. Now we saw earlier an example of the forward pass and the backward pass. The result is that each weight gets a gradient telling us how to adjust it to reduce the loss during gradient descent. Now let's give an example with the one neuron neural network, and we're going to do backpropagation on it, right? So recall during the forward pass, the network computes activations of each layer and stores them because the backward pass, backpropagation, needs these values to calculate gradients efficiently using the chain rule. So we've got X, W, XW, that combines. And then we've got B. To get Z is equal to XW plus B. Okay? W is the weights, B is the bias term. Okay? Now we're going to use a sigmoid function. And recall from the chain rule, we used this we calculated its derivative, right? So the y hat equals the sigma z 1 over 1 plus e to the negative x, right? We need to squash things to a 0, 1, okay? So we use that to calculate y hat. And then in order to calculate the loss, we introduce the actual value y. We take y minus y hat squared, okay? Now we want to go and do the backpropagation layer. What we do is we take the derivative of the loss with respect to y hat. So that's 2y hat minus y. And recall, if we take the derivative, okay, of sigma, we get this term. We found this in the chain rule with respect to z, okay? It's y hat 1 minus y hat. The derivative of y hat with respect to z is equal to that, y hat 1 minus y hat. Sorry for being repetitive, but I'm just trying to emphasize that. So if we go up, we take the partial derivative of z with respect to w, that's x, okay? The w term cancels out. And then the partial derivative with respect to the bias is just 1. So if we follow that term from z equals xw plus b to xw to w, we use all the partial derivatives that we've collected, okay, up to this term. I mean, the derivatives, and then we combine that into one term, right? So we started in the beginning with the loss, the derivative of the loss with respect to y hat. And then we followed it to y hat with respect to z, right? And then finally z with respect to w. So we get that term, 2y hat minus y times y hat 1 minus y times x. And if we follow it through the bias layer, we start at L with respect to y hat, same as before, y with respect to z, okay, because it has to go through the z. But this time we do z b is equal to 1. So we get 2 times y hat minus y times y hat 1 minus y hat times 1. So let's put some numbers to this just to clarify things. So we'll define what we saw earlier. We saw that wx plus b is equal to y hat, and then the loss is equal to y hat minus y squared, right? Y hat's what's generated by our neural network or model, right? And we've got x is equal to the input, y is equal to the true label, and wb is equal to the parameters we want to learn. So this is how we would set up the forward pass, right? We've got x is equal to 2, y is equal to 5, w equals 3, b equals 1, okay? And then in our first step, we would calculate the y hat, which we saw earlier. 3 times 2 plus 1 is equal to 7. And then we've got the y, 5 minus 7, I'm sorry, 7 minus 5 squared is equal to 4. The output loss is equal to 4. In the backward pass, we'll find how much each parameter contributed to the loss. In other words, compute the gradients. And that was the loss with respect to W and the loss with respect to B. And we start from the loss, right? We calculated this earlier, 2y hat minus y. And then at our values, we get 2 times 7 minus 5 is equal to 4. We go to the linear part. We take the partial derivative of y hat with respect to W, the derivative with respect of y hat with respect to B. It should be the derivative. Now we apply the chain rule. L with respect to y hat times y hat W is equal to 8. The loss with respect to the bias is equal to the loss with respect to y hat times y hat with respect to B. And that's equal to 4. So you notice it's only the parameter, the derivatives of the parameter that changes, but we're all starting with the loss, right? And then we've got loss with respect to W is equal to 8, loss is equal to B, loss with respect to B is 4. And then we use the gradients to update the parameters in the direction to reduce the loss, okay? So these are the gradients here. And the learning rate is 0.1. So if we multiply that out, we got 3 minus 0.1 times 8 is equal to 2.2. 1 minus 0.1 times 4 is equal to 0.6. I want to make sure that the x, you realize where we're getting some of our calculations. X is equal to 2, right? Wx plus b. And after this, the network will predict closer to y is equal to 5 next time. So we did one iteration. The forward pass, we compute z is equal to wx plus b, then y hat, and then the loss. The backward pass, compute the derivatives, the loss with respect to w, the loss with respect to the bias using the chain rule. And then finally, gradient descent. If you apply it immediately, it's w minus eta, the loss with respect to w, and the same for the bias, okay? But replacing the loss with respect to beta. I mean bias, sorry. So if you want to actually train the network, you repeat this times, right? The forward pass, the backward pass, and the update over all your data, sometimes in batches. That sequence of forward and backward and update is often called an epoch or an epoch, right? This is something that people should be familiar with if they've worked with machine learning before. We would do this until we find the optimal values for W and beta, and eta is the, and I'm sorry, bias, and eta is the learning rate. So we want to find the optimal values of W and beta, bias, that optimize the loss, right? Meaning minimizing it. So that's going to be it. Thank you very much, and I hope you have a great day.